Good morning, everybody. Happy Monday. It's been a while since I've seen you guys. You guys, of course, had a short week last week, and then we didn't have class. So we can start with some green check marks and let me know how you are doing. That'd be great. I also wanted to maybe discuss the learning guide, and I know Mrs. Ward gave you guys some practice provincial exams at the last field trip, so just wanted to speak to that as well. But yeah, just check in for now. Yeah, we're still on Unit 8. We have one section left. We'll do it this morning, probably take maybe like about an hour or so to get through it all. Hopefully. It always takes longer than I think, but it's graphing, and you guys have practiced your graphing skills in math already, so you guys would be experts already on this stuff. And then we get into Unit 9, which is on acceleration, which is just more of the same stuff. It all looks the same, and on the provincial exam or on a test, everything looks the same. So there you go. All right, so everyone's good. Perfect, clear those out. What I want to do is maybe just look at the course and just point out a few things. And we basically only have about... Okay, perfect, Taylor. We'll get to those. We only have, about 3 classes worth of material left, or 3 lessons left, and then we just have some review, and then the provincial exam. So everything kind of just happens really quickly now through the end of the course. So if you're in the course, we're on Unit 8 right now. We're going to cover graphing motion here today. And then once graphing motion's done, then we're going to jump into Unit 9, which only has 2 sections. So it's super, super quick, and that'll be Unit 9. So we'll definitely finish the course. I hope to finish the course this week. We'll finish Unit 8 and 9 this week. So there you go. And then Unit 10 we've done already. This was Earth Science, continental drift, and all that stuff. So really just Unit 9 left. The very bottom, you'll see this provincial exam section, and there's some different things here for you guys to go through if you want. I'm not going to make any of them mandatory yet. So final review vocab. This is just a PDF of all the vocabulary terms that we've covered so far this year. So I'm not a huge fan of just memorizing definitions and words, but if you go through that and it's I forget if it's I might as well open it up. If it's alphabetical or if it's broken down by unit. I think it's broken down by unit. No. Oh, yep. Biology, chemistry, physics, earth science. Perfect. So broken down by unit. So if you go through that and you see a word, you're in chemistry here, and you see something like, indicator. I don't remember what an indicator is. So maybe that's worth going back and looking at that, trying to figure it out. All that stuff's there. So those are all the important vocab words that you'll need to know. Like I said, not worth memorizing them all, but I mean, if you see something you've never seen before, then it'd be worth looking it up. The other thing we have here is a topic checklist, which is exactly what it sounds like. It just goes through each of the kind of learning outcomes from the course, and you should be able to do all of these things, such as use standard atomic notation to identify the atomic number and mass of various isotopes. So do you know what an isotope is? Atomic mass number. So you can go through that, and again, if you see something that maybe you haven't seen before, then you could go back and look it up. So the provincial I gave to Mrs. Ward to give to you guys was an old provincial I had, and that's this guy right here. It's called Practice Provincial. Now, I'm not going to insist you do it right now, but what I want to do is I want you guys to have it. If you didn't go to the field trip on Wednesday or Thursday last week, you didn't grab one, that's fine. You can just download it, but it's kind of long. Obviously, like 80 questions, multiple choice. Some pages only have 1 question on them just because of diagrams and whatnot. So it was just there for you guys to not have to print off as much. And I mean, you don't even really need to print it off if you have a digital copy, but it's nice to work off paper. So if you open that up and start going through those questions, then it's good to kind of, look at the questions, how they're asked, get used to the format of the exam. They're always the same. Yep, Taylor, it's 80 questions. The questions from each kind of section don't really change. So the number of questions from chemistry and biology, it's always the same. They just kind of change the questions a little bit. So it's worth just flipping through for now. The one that I gave you guys, and this one here, Practice Provincial, this is the one I'll go through with you in class. We'll go through it question by question. I'll give you some hints on how to get rid of, a few answers usually and things like that. And then if you click on this other one, Practice Provincials, this is just links to the 4 sample exams that are online on the BC Ministry website. So you can go to the BC Ministry of Education website. If you just Google BC Provincial Exams, it'll come up, and then you will be able to access all 4 of these exams and answers to those as well. I have an answer key for the exam I gave you, but I want you guys to go through it first without looking at the answers and then come back after and check the answers. So I'll put up a key to the exam I gave you maybe at the end of this week or beginning of next week. And there you go. Kind of a weird time, right? We're trying to review for the provincial and then finish up our course material at the same time. And it can be a lot all at once. But we're just going to zip through the end of the physics unit, and then we'll have time to just focus on reviewing. But there's not really a lot of classes left. We do like 2 or 3 classes a week. There's only 3 weeks left before your exam. So kind of crazy how fast the year goes. So that's that. I'm going to spend more time talking about the exam and the types of questions and things like that once we get through the course material, but I just wanted you guys to have that exam and access to it, and we'll start talking about it maybe at the end of the week, depending on how far we make it. So the practice exams and the exam that I've given you are always the same 80 questions and multiple choice, no written or anything like that. No short answer, no long answer, 80 multiple choice, that's it. So there you go. Taylor had some questions from Unit 8. Maybe we can get to those now. And I would be happy to go through them. Or if anybody else has any questions. So we've basically finished up to page 5 in the data or the learning guide. And we're going to talk about graphing motion today, which is page 6, 7, and then that's it. So there's only kind of 2 pages left, and we haven't talked about them yet. So anybody else have anything? Page 5, 13, and 15. What's the average velocity of a car that moves 60 kilometers in 3 hours? Okay, look at number 12 on page 4. Yes. All right, 13, 15. How far can 25 minutes at 12 meters per second? I'll just give you the formula for 13, and then I'll do number 15 for you. So the average velocity formula is on the back of your data booklet. So VAV, average velocity, is your change in position over your change in time. And you have your change in position is 60 kilometers. So that goes on the top here. And then 3 hours goes on the bottom. So 60 divided by 3 is going to end up with 20 kilometers per hour for that guy. Number 15 is a little trickier because we have some units to watch for here. We have 25 minutes and then 12 meters per second. We need to be careful that we're using the correct units and that they match up. So I have the data book here. Maybe I'll just jump back. We're asked to find how far, and that is a distance. So we need to know what the distance is. So if we go to our data booklet, you can see I've even highlighted it because the last question we looked at was the same thing. So the distance equals the velocity times the time. So we're going to use that. D is VT. Now, we're either going to have to convert minutes to seconds or 12 meters per second to meters per minute. Now, we never really talk about meters per minute. That doesn't really make sense. We're meters per second or kilometers per hour. So I'm thinking the easiest bet here is to convert 25 minutes into seconds. And then once we've done that, we can plug the information into the formula. So if we have 25 minutes, we want to get rid of minutes, and we want to end up with units of seconds. So if I have minutes on the top, I want to get rid of it. I'm going to put it on the bottom, and I want to end up with seconds. So I'll put it on the top. Now, what is the relationship between minutes and seconds? Well, hopefully we remember 1 minute is 60 seconds. We're going to use this unit cancellation type thing to figure out how many seconds are in 25 minutes. So we're going to go 25 times 60. We're going to end up with 1,500 seconds. And we have minutes canceling minutes, and we're left with seconds. All right, from there we can say, okay, we have our units matching up. I have seconds here, I have seconds here. That's a good thing. So I will take my velocity, which is 12 meters per second, and I'm going to multiply by my time. Now my time was in minutes, but now I've converted it to seconds. My S's are looking like 5s this morning, and I'm confusing myself. 1,500 seconds. And I'm going to end up with 1,500 times 12, which is 18,000 meters. Now we can say 18,000 meters, there's nothing wrong with that. It doesn't give us a direction to deal with. We're just assuming everything is kind of positive, and we don't know what positive means in the particular question. So 18,000 meters is fine. We could write 18 kilometers as well. That would be an acceptable answer. When we get really big numbers in meters, sometimes it makes more sense to convert it into kilometers, just divide it by 1,000. And sometimes that happens on exams and quizzes. You'll get an answer in meters like we've just done, but all the multiple choice answers will be in kilometers. So you'll get 18,000, but there'll only be an option of like 18 there. So just watch your units, it's really important. Hopefully that helped. Number 12, page 4. Displacement is change in position between 2 seconds and 5 seconds. So here we are at 2 seconds, and here we are at 5 seconds. So this guy went from here, moving across to there. So at 2 seconds, he was at 2 meters, and at 5 seconds, he was at 7 meters. So usually when we write down displacement, the actual definition for displacement, it's a vector, so sometimes you'll see a little arrow over top of it like that. It's a change in position. So it's your final position minus your initial position. And we haven't written anything like that before. And if you don't want to think of it in terms of that, that's fine. You can just think about where did he end and where did he start? And what was the change? How far did he go? So if I started here, I've got 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. And what direction? That was 5 meters to the east. That's all you really need. Or you could talk about something like this. You had 7 meters minus 2 meters is 5 meters, and then you look at the direction east. Doesn't really matter how you get there, as long as you are coming up with something like that. That's good. Now I'm just reading this last question asked here. For some questions that we don't talk about directions, such as 18 page 5, they still put a positive sign in the answer. With questions like this one, number 18 here, there's no real mention of direction and everything's just positive, so that's fine. If the question doesn't give you any direction, you can't give a direction. If all of the numbers you're given are positive, then your answer's positive, then that means that your answer is in the same direction as the initial sort of parts of the question. If your answer is giving you a negative, then that means you're going the opposite direction that was originally happening, but you don't know what that direction is. You don't know if you're going now south and everything in the question was going north. So given a question like this, you can't be really specific with your answer just because you don't know. You don't have to make up a direction. You can only use the information you're given in the question. So you don't have to get too carried away with direction. If no direction's given, then you can't just make it up. So there you go. It's just kind of one of these things that we can only work with the information you're given. Hopefully that's okay for that. I'm going to go through the graphing stuff, and then we'll come back to the learning guide, and we'll just take a quick peek. And if you have any other questions, we can go through them. So we're going to jump to 8.3. My laser pointer here. All right. This is graphing motion, and I've said this before, but you guys are really good at graphing, so you guys should have no issues with this stuff at all. At least I hope. And yeah, it's pretty straightforward. So time interval and position, we're going to talk about these things together. So initial time is when an event begins, and then final time is when an event ends. Now we use these little i's and these little f's, they're subscripts. Ti is the initial time and tf is the final time. One thing that I will mention that if you continue on and take physics with me next year, assuming I'm teaching physics next year, sometimes textbooks and teachers won't use I for the initial. Sometimes we'll use a little zero, and it's called T naught or T initial. So they mean the same thing, it just depends on who your teacher is and the notation they're going to use. Sometimes it'll be Ti, and sometimes it'll be T with a little zero next to it, but they both mean the same thing. So just a kind of a notation type thing. The time interval is the difference between the initial and final time. So you always go final minus the initial. Wherever you ended minus where you began in terms of time tells you how long the event took. So we've looked at this little skateboarder already, just in the last question. And it's the question I'm asking you guys is, what is the time interval to move from the hydrant to the sign? What's the time interval? Almost the exact same question we just looked at. So how long did that take? Any ideas? Now with questions like this, the numbers are really small. You can just work it out in your head. Perfect, Haley, thank you. 5's right. But what you're actually doing is you're taking the final time. 5 minus 2. Sorry, Taylor. You're taking the final time, which is 5, minus the initial time, which was 2. So 5 minus 2 gives you 3. So the event took 3 seconds. Even though at the sign, you're 5 seconds, the event, which is from the hydrant here to the sign, only took 3 seconds because you're at 2 seconds, 3, 4, 5. Now you're here. So 5 minus 2 gives you 3 seconds. So that's what you're doing in your head. 5 minus 2 gives you 3. So that event took 3 seconds. If we wanted to know from the tree to the sign, that would be 5 minus 0, which is 5, and that event would have taken 5 seconds. And what we don't want to do is, I think what you're doing here right now, Taylor, is you're kind of confusing your position and your time. And the question is just asking about time. So it doesn't even matter where this person is, how fast they're going, anything like that. So don't confuse yourself by mixing up the distance, position, anything like that with the time. It's just asking about time. So you could just go, okay, at the hydrant, that was 2 seconds. At the sign, that was 5 seconds. 5 minus 2 is 3. It took 3 seconds. It doesn't matter where he was. 2 meters here, 7 meters here, has nothing to do with the time it took. So try not to confuse the values. Moving on. We're going to talk a little bit about uniform motion, more so after the break, but for now, it's the definition. So a uniform motion is an object that's not speeding up or not slowing down. It's traveling at a constant rate. And a lot of times in physics textbooks, you'll see pictures like this, where what they basically do is they turn a camera on in a dark room, and then there's a strobe light, and the strobe light flashes at a constant rate. So the ball's moving across the table, and every time the strobe light flashes, light hits the ball, and then gets developed on the camera. So it's a really, really good way of being able to figure out how far an object's moving in a given amount of time, because a strobe light will flash, every whenever. If you want it to flash 5 times per second, you can set it to flash that many times. But it's not speeding up, it's not slowing down, and it's not changing direction. This is the important part of uniform motion. So uniform, whatever that means to you, uniform motion is just an object that's moving the same amount of distance in the same amount of time. So how can we tell from the picture here if the object's moving in uniform motion, or if an object weren't moving in uniform motion, what would that look like? So how could we tell the difference between uniform and non-uniform motion, given an image like this? Any ideas? How can we identify uniform motion in this picture? Or if uniform motion were not happening, what would that look like in a picture? So it wouldn't have equal distance. That makes sense to me. So each flash, the ball is about the same distance apart for each flash. So this distance is the same for each one. So if it were traveling, if it were speeding up, then the flashes happened at the same time, but the balls would actually be a little bit further apart. So this ball would maybe be over here a little bit. And same if it was slowing down, the balls would be a lot closer together. They wouldn't be as far apart. So yeah, perfect. We'll actually look at an example of that here in a second. So there you go. That's uniform motion. We're going to talk a little bit about graphing. And one kind of tricky thing that happens is we're going to spend some time talking about position time graphs. So plotting an object's position as a function of time. So at any given time, where is the object away from some point? Now, we're going to spend a bunch of time talking about position time graphs, and then all of a sudden we're going to talk about velocity time graphs. Now, in class, it makes sense. Everything we talk about now is position time. Everything we talk about later is velocity time. But on a test or a quiz, it gets really tricky because sometimes you'll be given a position time graph, and then the next question will have a velocity time graph. And you need to be able to think, what is this graph showing me? So make sure, please make sure when you look at a graph, you always check the units on the axes. So is it a position graph versus time, or is it a velocity versus time? Most graphs will have a nice title, like this one does, position versus time. If they don't, you'll be able to identify a position on this side and then time down on the bottom here. So it's really important that you're able to identify the difference between the two, and all that means is just reading what it says. And it seems really obvious, Mr. Borden, why would I make a mistake and confuse these graphs? When you're kind of, head down, flying through a test, you see a question, position time, velocity time, you're not reading your units very carefully. It happens a lot. So the position time graphs always look the same. They have position on the vertical or y-axis, and they always have time on the horizontal or x-axis. This best fit line is really important. Jumping all over the place here. Best fit line is really important, and it's not actually shown here. And I'm going to have to show you what I mean by best fit line. So remind me to do that when we jump to the learning guide later. I'll draw some diagrams for you and show you what a best fit line is. Uniform motion is represented by a straight line on a position time graph. So if we have a straight line, that means we have uniform motion. And we can get lots of information from this graph, and you guys are well aware how to do that, so I'm not going to spend a ton of time talking about it, but we'll maybe just look at some examples. So we can end up with kind of 3 different scenarios, and this is just the exact same as the last stuff we did in math class. The position side, what does the right brackets mean? The right brackets. I think it has, the word right, that's just telling you the object's moving to the right. So it could say left in there, it could say up, it could say down. It could also have like a north, south, east, west in there. It's just indicating direction, which is, I could see why that would be a little bit confusing. So yeah, just the object's moving to the right. So 3 scenarios. You could have positive slope, which goes up to the right. Up to the right, it's backwards for me. You could have zero slope, which is a horizontal line. And then you can have a negative slope, which goes down to the right. So what do we think a positive slope means? Looking at the first graph up at the top here, you see that it has a positive slope. It's going up to the right. If we were to describe this motion, what would we describe as happening here? How would we tell somebody what was going on in this graph? It's one thing to look at a graph, but it's another thing to understand what's going on there. So if you had to explain this to your little brother or sister, what would you say was going on there, the first graph? In a couple words, doesn't have to be super elaborate. It's going up. So if those brackets said centimeters left, then the negative slope would actually be to the right. Ooh, that's going to be the 3rd example, so we'll definitely get to that, Abby. It's going up. That's a common thing that students will see happening on the graph here. What does it really mean though? We have position in centimeters to the right. So at 0 seconds, I'm at 0 centimeters to the right. After 1 second, I'm at 20 centimeters to the right. And then 2 seconds, I go up and across, I'm at 40 centimeters to the right. 3 seconds, I'm at 60. 4 seconds, I'm at 80. 5 seconds, I'm at 100. So is the object moving up, or is it moving in some other direction? It is, in fact, a positive slope, and it is increasing its position, but is it going up? Is it moving off the ground? Is it going in the direction up, or is it going in a different direction? A little bit tricky, I guess. So the graph here is telling us that this object's moving to the right. So when we see that the line is increasing in terms of slope, or going up and to the right, the actual object isn't moving to the right. The object is starting at 0, then it's moving to 20, 40, 60, 80, and 100. So the object's basically, you could think of it as kind of like a ball, or my little laser dot here, and it starts right here, and it's just moving to the right with uniform motion. So the object isn't going up, it's just moving to the right. How about the horizontal line, or 0 slope? Again, if you were to describe what was going on here, how would you describe what was happening to somebody? The second graph, horizontal line, what does that mean? What is the object actually doing? And think about it in the same way I just looked at the other one. If you're at 0 seconds, where's the object? If you're at 1 second, where's the object? If you're at 2 seconds, where's the object? This one's maybe a little bit confusing. Nobody wants to take a stab at this one. It's actually quite straightforward once you really think about it. Of course, this is the first time you've seen it. All right, so at 0 seconds, the object's at 2 meters to the right. At 1 second, the object's at 2 meters to the right. At 2 seconds, the object's at 2 meters to the right. At 3 seconds, the object's at 2 meters to the right. 4 seconds, 5 seconds. You get the idea. The object's not moving. It's completely stationary. Perfect, Ava. So it doesn't matter what the time is, the object's still at the same spot. 2 meters, 2 meters, 2 meters, 2 meters, 2 meters, 2 meters. So the object's always 2 meters to the right. So if you see a horizontal line on a position time graph, that means your object's not moving, which is different than a velocity time graph, which we'll get to here in a second. The negative slope, the last picture here, and Abby kind of alluded to this before. We've done positive slope up and to the right. We've done horizontal line, now negative slope. What's going on? If you had to describe this to somebody, what would you say the object was doing? So think about it like we've done the last two. At 0 seconds, you're 1.5 meters to the right. At 0.2 seconds, you're 1 meter to the right. At 0.4 seconds, you're half a meter to the right. And then at 0.6 seconds, what does it mean when it crosses the x-axis here? What does that mean? And then at 0.8 seconds, you're negative half a meter. And now anything above the axis here is to the right. Anything below the axis is going to be to the left. So you're half a meter to the left. At 1 second, you are 1 meter to the left. So what was going on, and Abby, you mentioned something before, negative slope would actually be to the right. Is that what's happening here? Is this object moving to the right? Or something else going on here? I mean, you can always draw a picture to try to figure out what's going on with this stuff. Like maybe a little stick figure or even just a ball, and just trying to figure out what's going on. So a negative slope is representing negative movement. Then would a negative slope represent a positive movement? Oh boy, we're getting deep now. All right, let's look at what you're saying here. So would a positive slope represent a negative movement? Then would a negative slope represent a positive movement? Yeah, I guess it's kind of confusing stuff. A negative slope just means the object's moving opposite to the direction indicated on the graph. So on this graph, it says going to the right. So if we see a negative slope, that means the object's moving to the left. Let's maybe draw a picture of this. I think I have this loaded in. Yes, I do. All right. Let's just maybe look at the last one here. Just supersize this a little bit. But it says to the right. All right. Let's start with some object. I'm going to start with a tree. There's my tree. And I'm going to say, I think you are, but you guys have never seen this before, so that's why we're talking about it. Your tree is at 0 meters. Are we happy with that? Does that make sense? So I'm going to have a kind of like a ruler along the bottom here. And my tree is my origin, or 0 meters. I guess I can just do this. Should be fine. All right, so there we go. So I have 0 meters. This is 0.5 meters. This is 1 meter. This is negative 0.5 meters and negative 1 meter. And I have some object. I don't know. Let's make it just a red ball. Now, guess I need 1.5 out here. Okay, so I have this red ball. At 0 seconds, my red ball is 1.5 meters to the right of something. Okay, we all happy with that? That's this point right here. 0 seconds on my x-axis. The object's 1.5 meters to the right. Okay, now 0.2 seconds passes. This is where I'm looking now. And my object is 1 meter to the right. So now my red ball's here. This is 0.2 seconds. What happened to the ball? Well, the ball is just kind of cruising along, going that way. It moved from there to there. All right, let's look at the next one. The next point says at 0.4 seconds, my object is 0.5 meters to the right. So here's my red ball. This is at 0.4 seconds. So again, the ball just is kind of rolling to the right. This point right in the middle where I have my objects crossing this axis, the x-axis, what does that mean? Well, at 0.6 seconds, my object is 0 meters to the right. So this is 0.6 seconds. And you can kind of imagine at 0.8 seconds, my object is 0.5. And then at 1 second, my object is at negative 1 meter. Does that make a little bit more sense to just describe the object moving like that? If we draw it out on a nice little diagram. So the object's just a ball rolling along. Remember, the negative sign is just indicating direction. Just means it's moving towards that tree, and then it moves past the tree. It doesn't stop at the tree. Nothing fancy happens at this middle point at this 0.6 seconds. It's just an object. It's kind of rolling along, and then it passes the object, the reference point. In this case, I drew a tree. It could have really been anything. I kind of get it, but you still put the ball in the left direction. I didn't choose that. That was indicated by the graph. Maybe I'll just scroll up here and we'll look at the one at the top. So this is a position time graph. This is the one that was at the top. There's the 3. So this is a positive slope. I'll just quickly draw what this one looks like. Let's have another object. Let's start with the tree again because my trees are pretty good. All right, so that's 0 meters. And then I have 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. I could do the same thing going to the left. Could have negative 1 meters, negative 2 meters. Get the idea. All right, let's draw our red ball here. At 0 seconds, the ball is at 0 position. All right, so this is at 0 seconds. Then I look to my next point here. At 1 second, my ball is, I did 2, but I should have done 20. Let's change the scale of my line here. 20, so this is 10, 20, 30, 40. This is negative 10, negative 20. Hopefully that's all right. So at 1 second, the object is 20 meters, and in this case, it tells us to the right. So my red ball is here, and again, that's at 1 second. It's 20 meters to the right. And then the next one, so my ball rolled to the right a little bit. The next one's here. At 2 seconds, my object is 40 meters to the right. So this is 2 seconds. And that's just going to continue. The ball is just going to keep going. At 3 seconds, it's going to be 60 meters. So if I had another point out here, there's 50, there's 60. Draw the red ball over here. And that would be at 3 seconds. So the ball is just moving to the right. That's what the positive slope is indicating. Now I don't want to confuse you, but it can get confusing. Now our graphs in the first example here said centimeters to the right. And I could just as easily have a graph that said centimeters to the left. There's no reason the graph couldn't be plotting an object moving to the left. Now, normally in physics, we think of things that are going to the left as being negative. But there's no reason it has to be that way. That's a completely arbitrary decision on our behalf. If you think about it, in North America, we read from left to right. That's just how we do things. But if you're in Japan, they read from the back of a book and they read from top to bottom. So it's just kind of like, well, they read from essentially right to left. They read backwards through a book. So maybe if I was teaching physics in Japan right now, I would have everything to the left was positive and everything to the right was negative. It's a completely arbitrary decision. We've just made this decision. It's not right, it's not wrong. We've just decided it's just going to be that way. So it's kind of where it gets a little bit confusing in terms of this stuff. So just be careful, watch your signs and watch what you're graphing, your units, things like that. So we've done positive slope. In this case, it was an object moving to the right. Negative slope, it was an object moving to the left. And then horizontal line, zero slope, just an object wasn't moving. It was just completely stationary. So those are the scenarios you're going to encounter. You probably knew it was coming. And when I was in grade 11, I took physics, and my physics teacher said, if you see a graph and you don't know what to do, find the slope of the graph. Just always. Every question you don't know what to do, you come to a graph, find the slope. That's going to get you almost guaranteed a mark in any physics question. The slope of a graph is always really important, and you guys spent a lot of time finding slope. Now, in math, we talked about slope being rise over run. And the rise was the change in the change in y over the change in x. Now, we're in physics, and we're not talking about x's and y's anymore. Now we're talking about position time graphs. So if you look at the slope formula here, this thing's so sensitive. The slope formula is change in position over a change in time, which is just the exact same thing as what you guys did in math. Except it wasn't change in d over change in t, it was change in y over change in x. You've already done this. I've just changed the letters from x's and y's to d's and t's. Now, you guys are really good at finding the slope. The only thing that's kind of getting in your way is students tend to get confused. As soon as you see d's and t's instead of x's and y's, they're like, it's so confusing. Abby, the arrows above the letters indicate that these things are vectors. So D is going to be position, arrow over top because the direction's important with that. Something like time, we don't have any way to indicate a direction for time. It's not a vector. So we don't have a little arrow over the top of it, which is a good question. It's just a notation thing. Some teachers will use it, some won't. I think it just confuses students, especially at the grade 10 level. It's just an extra thing in there that you don't really need to know for the questions you're doing. Even when I was in university, my professors didn't really insist on the arrows. It's just kind of assumed if you've made it that far. So I'm not going to spend a ton of time describing this formula, but we're just going to maybe do a couple examples. I will for sure, Taylor. We'll look at them. let's, instead of doing like a calculation, let's just talk about in terms of like an idea. So we have two joggers here. We have a position time graph. We make sure always check our units. So we have position, meters forward. We don't know what direction it is, just forward. And then time. So we definitely have a position time graph, and you can see the title even says position time graph, which is really important. We have jogger A and we have jogger B. And we can look at the relative slopes of these two lines. So jogger A, jogger B. They're both starting at 0 seconds and 0 meters, which is kind of seems strange, or doesn't seem strange, I should say, but we'll look at some examples of when that doesn't happen. What is the difference between these two joggers? Who is faster? Who's slower? What other information can we get from the slopes of these lines? Maybe instead of thinking about calculating the slope in terms of numbers, we'll just look at the slopes compared to one another. Which one's steeper line? Which one has a steeper slope? Jogger A or jogger B? And then we'll kind of figure out what that means, maybe. So no numbers yet. Steeper slope belongs to jogger A, jogger B. Jogger A, jogger B, jogger A, jogger B. Jogger A is going faster because the slope is steeper, question mark. I think you should have just lost the question mark there, Ava. But let's look at it. Okay, so jogger A here. Jogger A was running 20 meters in 5 seconds. So I go across 20 meters, 5 seconds. Jogger B ran 16 meters in 8 seconds. Let's maybe pick a point that crosses both these. At 5 seconds, where was jogger A and where was jogger B? So we know they both started at the same spot at 0 seconds. At 5 seconds, jogger B was at 10 meters, and at 5 seconds, jogger A was at 20 meters. So jogger A has a steeper slope. That means jogger A ran 20 meters in the same amount of time that jogger B took 10 meters. So 5 seconds, jogger B is at 10 meters. 5 seconds, jogger A is at 20 meters. So clearly jogger A is faster because jogger A is moving a greater position or greater distance in the same amount of time. Hopefully that makes a little bit of sense. All right. I'll talk about velocity. Yeah, let's do this. We'll talk about velocity, and then we'll maybe take a break after this. There's about 3 or 4 more slides left. So average velocity. The slope of a position time graph is the object's average velocity. So slope is velocity on a position time graph. Like I said, if you don't know what to do, you're given a graph, you find the slope, that's going to mean something to somebody, probably going to give you a mark. Again, I'm going to look at the graph. I'm going to make sure I know what type of graph it is. So I can see that it's a position time graph. I have position on the y-axis and time on the x. It even says position time. You'll see a lot of graphs like this. They don't actually have numbers. This is T1, T2, T3. I got to quit doing that. You can make these times whatever you want. You can make this 5 seconds, this 10 seconds, this 15 seconds. It's not important to the question. The graph is just saying, at this time interval, the object's here. At this time interval, the object's here. And at this time interval, the object's here. We don't always have to put numbers on these things. Sometimes numbers just confuse us. So what's going on? Could we describe what was happening to this object without numbers? I don't know how far it's going, but could I describe kind of general or relative motion here? At 0 seconds, it started at the beginning, which is 0 position. I have a positive slope. I have a horizontal line or 0 slope, and then I have a negative slope. What is going on with this object? We know what a positive slope means. In the example we looked at before, that remember the ball was moving to the right. And then a horizontal line or 0 slope, the object was stationary, not moving. And then a negative slope, the object was moving back from where it came. So if I were to describe the object here, I'd say the object was moving away from where it started. Maybe then the object took a little break, and then the object moved back to where it started. At 0 meters, 0 seconds, or 0 position, 0 seconds, at t3, it's back to where it started. It has the same position. So again, objects rolling away from the initial position stops, and then the object's rolling back to where it started. We're going to actually calculate the slope here, and I promise eventually. So a positive slope, it's moving away. 0 slope, not moving. Negative slope, moving back to where it started. And we'll talk about how to find average velocity from a graph. Now, calculating average velocity is change in position over change in time. Distance is the velocity times the time, and then time is the distance divided by the velocity. So before we were looking at questions, they didn't really say which formula to use, but if it said, how far has an object traveled, you say, okay, how far? I'm going to use the distance formula because it's asking me to find how far. Or if it said how long, I'm going to try to find time. And again, these are all in the back of your data booklet, these 3 formulas. We've seen them before. We're just looking at them in a new light now. All right, let's do some examples. We have 4 lines here, A, B, C, and D, different colors. And we are asked to figure out which one has a slope of 1, which one has a slope of 2, which one has a slope of -1, and which one has a slope of 0. So let's maybe start with the easy one. Which line has a slope of 0? That's probably not too difficult. Just throw the letter into chat. 0 slope. We have a C. Have any other votes for C? Another vote for C? Okay, that was the easy one. C has 0 slope. Now, this is where it might get a bit tricky, but I think you guys can handle it. The other ones are asking for a slope of 1, 2, and -1. But I don't have any numbers to deal with. I don't know what my distance is. I don't know what my time is. So how can I actually find a slope? Well, I'm just comparing them, right? I don't need a specific value, but I can say, okay, if C is this, then maybe A compared to it is this. -1 is D. Okay, a negative slope is down to the right, and D is definitely going down to the right. So that would be negative. I would agree with you there, Taylor. Anybody disagree with that? Are we happy with the negative slope there? Now, the next 2 slopes are 1 and 2. Yes, Abby, distance time graphs and position time graphs are generally the same. Yes, just for the purposes of what we're doing, yes, they're the same thing. I don't know what's 1 and I don't know what's 2, but I can compare A and B to one another. And I can say, okay, A is a little bit steeper, B is less steep. Wouldn't it be B because right under the 0 for -1? Remember, Ava, we're talking about slope here. So it can be, if we even look at A here, you can see it goes down a little bit into the negative in this quadrant here. It's still, the slope is going up and to the right. So if we were talking about something like position, you might be right. But in this case, we're talking about slope. So the slope of the line is the rise over the run. So if I look at A, it looks like it's about twice as steep as B. A is going to be 2, B is going to be 1, just relative to one another. Second example here says, what would it mean when a distance versus time graph shows a negative velocity? I'm actually going to jump over here and scroll down. There we go. So I can write negative velocity, distance versus time graph. Let's maybe just draw a graph quickly. It doesn't have to be pretty. Of course, you guys always use a ruler when you draw your graphs, but I am not going to. So there's the distance time graph. What would it mean if we had a negative velocity? Now, I kind of just glossed over a point, but it was really super important. And I said the slope of a position time graph is your velocity. So how would I indicate a negative velocity on this graph? What would that look like? A negative velocity would indicate a negative slope. So if I wanted to draw a graph, a position time graph with a negative velocity, I would have to have a negative slope. So I could draw a line like that. There we go, a little line segment. That definitely has a negative slope. It's going down and to the right. So that means it would be a negative velocity. Okay, let's look at a few more examples. I really like this example. I think it's a good one. Following data were graphed for a 100-meter race between Bob and Ed. Everybody's favorite runners, Bob and Ed. Again, if you were to describe to somebody who wasn't at this race, again, your mom, dad, little sister, brother, what was going on? What's happening at the race? You can tell a ton of information from this graph. So it's a 100-meter race. I check and I see that I have a position time graph or a distance time graph. Same deal. A distance versus a time. Okay. What's going on here? Bob's the red line, Ed's the blue line. I need to describe what's going on to somebody who's never seen this race or doesn't really know what a position time graph is discussing. So, first of all, maybe let's go with who won the race. Who won, Bob or Ed? It was a 100-meter race. Here's 100 meters up at the top. Who won that race? Bob or Ed? Any ideas? Ed catches up to Bob. Ed did catch up. Ed won the race. Who thinks Bob won the race? We have one vote for Ed, and Ed's catching up to Bob. We'll get to what that means in a second here, Taylor, because that's super important. I would look at my graph and I would say, okay, I'm interested in 100 meters. It's a 100-meter race. So I'm going to go to 100 meters. I'm going to go across on this line, and I'm going to see who got to 100 meters first. Now, it kind of looks like both lines are at the same point at 100 meters. And if somebody asked, I would say, okay, that 100 meters took them 10 seconds. If I didn't have this red line, if I took out Bob's line, you would say it took Ed 10 seconds to get to 100 meters. Okay, now I'm going to look at Ed's line. Bob's line. I'm going to get rid of Ed's line here. And I would say, okay, it took 10 seconds for Bob to get to 100 meters. So if I looked at each of the lines individually, they both end up at 100 meters at 10 seconds. It's a tie. Both runners get to the finish line at the same point. But Taylor said something really important earlier. She said Ed catches up to Bob. What does that mean? How do we have different slopes? We have two runners running a 100-meter race. How could somebody catch up to the other guy if they're both crossing the finish line at the same time? There's something really important in your statement, Taylor, Ed catches up to Bob, that we need to kind of discuss a little bit further. One of the slopes is clearly steeper than the other. Ed, his slope is steeper than Bob's slope, meaning Ed was running faster because the slope of the line is the velocity. So how can two people finish a race at the same time and they could be running at different speeds? Because their slopes are different, that means they're running at different velocities. What important information have we not discussed yet in terms of this race? What do we think? Bob's start. You want to elaborate a little bit further on that, Taylor? Because you're completely right. What was special about Bob's start. Taylor's now a little bit closer. You guys are both right. You're on the right track. Bob didn't start at 0. Bob, what are you doing? All right, so this is 10 meters here. This is 20 meters. So at 0 seconds, Bob was right here. Bob got a 20-meter head start. Not Bob. Ed started at 0 meters at 0 seconds, but Bob started at 20 meters at 0 seconds. So Bob got a 20-meter head start. Maybe Bob was old or something and he needed a head start. Or maybe he cheated and started 20 meters down the race course. Bob he only ran 80 meters. He started at 20 and he finished at 100. That's only 80 meters in there. So he didn't actually run a 100-meter race. That's why his slope of Ed is a lot steeper, because Ed ran 100 meters. He had to run faster because Bob got that head start. I love this question. It's a great question. It really makes students pay attention to the axes, what they mean. And if you're kind of understanding that Bob got this head start, you're understanding what the points on the graph mean, which is a good thing. All right, let's look at a couple more examples here. And I don't want that. I want that. All right, so let's think about this. Similar scenario, but maybe a little bit different. A blue car was driving at 60 kilometers per hour. A red car was driving at 100 kilometers per hour past that blue car. What would this look like on a distance versus time graph? And how would we know when a pass occurred? What special thing would happen on a graph when the blue car got passed by the red car? What would that look like? Would it be an intersection of one of the axes? Would a line cross something? Maybe if you have a piece of paper in front of you, just draw a little quick graph and see if you can figure out what a distance versus time graph for something like this would look like. So you have a blue car driving at 60, gets passed by a red car at 100. What special thing will happen when the cars passed each other? What would that look like on a graph? How could I indicate that on a graph? I actually have some video footage of the car race here. I have a blue car and then a red car. Zoom. All right, so my blue car traveling at 60 kilometers per hour. The red car is traveling at 100 kilometers per hour. Now, it's not really important that the blue car starts at 20 meters, and it's not important that the red car starts sometime after, but what is kind of important is the red car enters the race about 4 seconds after the blue car. And when the cars intersect right here, which is the same thing as right there, at 60 meters, they both are at the same spot, which also happens to be 7 seconds. So 7 seconds after the race began, the cars are at the same spot. But because the red car is going faster, it actually passes the blue car. So, you couldn't figure out how they figured out how far it should start ahead. I guess it's not really important. As long as you're just trying to figure out what's happening, you're always going to have two lines that cross. The important thing here is the slopes of the lines. The blue car had a speed of 60, so it should have a slope of 60. The red car had a speed of 100, so it should have a slope of 100. So if you have your blue line and then your red line should have a steeper slope, And it doesn't really matter how long of a head start you gave it. If you drew that red line here, it would just pass it a little bit sooner. If you started your red line at 8 seconds after, you'd have the same slope, but the lines would just cross a little further along. So that's what's happening in this little example. Okay, let's see if you guys have put all these pieces together. Is anyone brave enough to describe what's happening in this graph? And if it helps, you might consider drawing a graph. I don't like this graph. It's in threes, and that bothers me a lot, but I'll get over it. 3, 6, 9, 12, 15, -3, -6, -9, -12. Okay, just draw a little sketch. Doesn't need to be pretty. I'm going to put my tree at 0 meters, and we're going to describe the motion of the object. Now, Taylor, one thing that is really important is that when you say it goes up, you're indicating a direction. Up is the direction. Now, just because the line is increasing in slope, does not mean the object's going up. And I think Anna said something like this before. It's super, super duper important that every time you see a slope that's increasing, you don't assume the object's rising in the air. That's not what this means on the graph. So let's look at the graph and figure out what's going on here. All right, so I have some 0 position. It's completely arbitrary. I've drawn a tree there. There we go. I've picked 0 position. At 0 seconds, I'm talking about this red portion of the line here. All right, at 0 seconds, where is my object? Anna, you're right. It has a positive slope, so it's going to the right. This says displacement. I don't have any indication of what displacement means, but I'm going to assume everything to the right is positive. And that's an assumption that I'm willing to make. So 0 seconds is this line here. Where does my object start at 0 seconds? Does it start at 0? Does it start at the tree? Or is something else happening here? This is kind of like Bob and Ed. One of them got a head start. Didn't start at 0 meters at 0 time. If I look at my graph, this is -3 right here. So at 0 seconds, my object is -3 meters. So here's my little ball, and this is 0 seconds. It's not starting 0 meters at 0 seconds. It's starting at -3 meters at 0 seconds. Okay, 3 seconds later, roughly, it's actually a little bit more than that, it looks like about 5 seconds, it's at 0 meters. So I'm going to draw the ball right here. This is at about 5 seconds. It's at 0 meters. All right, let's keep going. At 6 seconds, let's find a nice spot here. At 12 seconds, it's at 6 meters. There we go. That's 12 seconds. So it kind of looks like my ball is rolling to the right. And Anna, you were right when you said, it's going to the right, isn't it? Perfect. All right, now my object is at this little horizontal line here. What does that mean? From 12 seconds to, this is 15 seconds in here, what is my object doing from 12 seconds to 15 seconds? It's not moving. Perfect. There's 15 seconds. There's 12 seconds. It's taking a break. It's just hanging out at 6 meters. All right. Now I have this green portion of the line that I'm looking at. At 15 seconds there, this is 18. So at about 15 seconds, the object moves to 12 meters. 9, 10, 11, 12, 13, 14, 15, 16, 17. So about 17 seconds, the object's over here. That's 17 seconds. Okay, let's look at this blue portion of the line. What does the blue portion of the line mean? I'll assume this is 25 seconds here, this last point. At 25 seconds, where does the object end up? Well, if I go across, it looks like this is 6, this is 9 meters. So now my red ball is here at about 25 seconds. So what does that blue line represent? Well, it represents a negative slope, which means it's going down to the right, which means a negative velocity. So instead of my ball moving to the right, to the right, to the right, it actually ends up moving back to the left, and this is where it ends. So what did my ball do? Well, it started at 0 seconds, it moved to here, took a little break, then it moved to here really fast, and then it moved back to here really slowly and stopped there. So move to the right, to the right, to the right, move to the right really fast, took a little break, and then back to the left. Hopefully we're starting to get the idea with this stuff. The last thing actually doesn't show up in this section, but I just wanted to point it out. We're actually going to cover it in the next section we have. So velocity time graphs kind of just pop up. All of a sudden, you've talked about distance or position time, distance time, position time graphs. And then all of a sudden I get to a graph that's velocity and time. And these are completely different. They mean completely different things. The slope means something completely different. A horizontal line means something completely different than a position time graph. If they were the same, we would just call them the same thing. They would all just be called position time graphs. But this is called a velocity time graph. Yeah, so Anna, you're 100% right. Everything we've done so far, talking about how objects are moving, we're just plotting it on a graph. And the reason we use graphs is because they can show a lot of information in a very small space. You can get a ton of information from a graph. We looked at the race of Bob and Ed. I wasn't there, I didn't see Bob and Ed race, but looking at the graph, I can see that they tied. They both ran 100 meters in 10 seconds, or got to 100 meters in 10 seconds. One of them got a 20-meter head start, didn't run as fast, so they finished at the same spot at the same time. I can tell exactly where each runner was at each given time, even though I wasn't there. So there you go. Velocity time graphs are completely different. We'll actually end up talking about them, but I just wanted to show why it's so important that you read the axes and figure out what's going on in terms of these graphs. So if I looked at, just really quickly, and we'll take a little breather, if I look at 0 seconds, the object's moving at 0 meters per second. These are all velocities now instead of distances. If I looked at 5 seconds, I go across, this looks like it's about, I don't know, what's that, 30, maybe 29, we'll pretend it's 30. What does that mean? Well, the object at 10 seconds is moving at 30 meters per second. Or 5 seconds, I should say. At 10 seconds, the object's moving at 60 meters. Oh, we're at meters per minute, which is weird. So here it's going at 0, now it's going 30, now it's going 60. So the object's speeding up. What's happening here? We talked about a horizontal line on a distance time graph. It meant the object wasn't moving. What about on a velocity time graph? At 10 seconds, the object's moving at 60 meters a minute. At 15 seconds, the object's moving at 60 meters per minute. This is 60 meters per minute as well. So a horizontal line on a velocity time graph doesn't mean the object's not moving. It means the object's traveling at a constant velocity. It's not changing its velocity. All right. Now the object's going 60, now it's going 40, now it's going 20, now it's going 0. Now it's going negative 20, now it's going negative 40. So what's happening here? Well, the object's slowing down. Now the object's going backwards. It's still going backwards, but it's slowing down going backwards. There's some crazy things happening here, and we'll talk about them all in a second. The important thing here is that you don't confuse the graphs with one another. Just because you have a horizontal line on a position time graph means the object's not moving. On a velocity time graph, it means it's moving at a constant velocity. There are very different things happening on these graphs, and it's important that you know the differences between them. If you get really confused, just draw a little picture. And it is confusing. Once you get a lot of experience with them, it becomes very easy, but for now, you've never seen them before. And they look the same, the lines look the same, everything kind of looks the same, but they mean very different things. So maybe we'll take a 10-minute break. It's 10:20. We'll take a 10-minute break, and at 10:30 we'll come back. We'll talk about section 9.1 a little bit. I have a feeling you guys have some questions about the learning guide, so maybe in 10 minutes we'll come back, have a quick look at the learning guide, and then I want to jump into 9.1 because I want to finish this material off, finish the course off this week. So we need to do that. Just keep rolling, and then I'll leave you guys with some work, and we'll go from there. So I'll see you guys back in 10 minutes. Get up, move around, grab a little drink, maybe some coffee, wake yourself up, a little snack, and we'll see you back in 10 minutes. Thanks. Hi guys, welcome back. If you could give me a green check mark, just so I know I'm not talking to myself. I'll go over a few questions from the learning guide, and then we will jump into section 9.1, just to kind of keep moving. I know, Taylor, before you asked about an actual slope calculation, and I said, yeah, I'll get to it, or maybe it was somebody else. I will get to it, I promise. I haven't forgotten about that. So, just looking at the learning guide, what page are we on here? So page 6 says graphing motion, and then we're going to look at a bunch of the different types of questions involving graphing. Now, you can be asked about things like slopes or like relative type questions, things of that nature. Sorry, doing two things at once. But the important thing is you just kind of understand what the slopes are. A positive slope, moving forward. Zero slope or horizontal line, not moving. And then a negative slope's moving backwards. The questions here from the learning guide are all talking about position time graphs or distance time graphs until you get to the question number 5. No. Yeah, they're all position time graphs. So I didn't mean to confuse you by showing you a velocity time graph. I just wanted to show you why it was so important that we know what the difference is, just so you don't kind of forget about it. So number 1 and 2 I think will be okay. This one's kind of a relative type thing. It's kind of like our race that we looked at before. I think you should be all right there. How did each runner take 10 meters? What's distance? Determine the speed of each runner. Show all the work. Let's look at number 4. It's actually asking us to find the speed of each runner. And we need to kind of find the slope here. So for question number 1, they only want us to explain it in relation to d versus t graphs. Yes, that's correct. Pretend like you haven't seen velocity time graphs yet. Again, I just wanted to show you the difference between the velocity time and position time graphs or distance time graphs. Let's look at this. I'm going to make this a little bit bigger just so we can see it a little bit more clearly. All right, it's asking us to find the speed of each of the runners. And remember, the speed is the slope of a position time graph. And in this case, we have jogger A and jogger B. And I will do one of them, and then I'll leave one of the others for you guys to do. Maybe I'll do jogger A. Here we go. So, jogger. So, jogger A, speed, which just really means the slope of the line. Now, slope is just rise over run, and if you can remember that from math, then you'll be okay. If you want to think about it in terms of physics, or what we've been doing, you'd have something like this. Average velocity is the change in position. I guess that's not the letter I was hoping for. Change in position over a change in time, which is just the same thing as delta y over delta x. In this case, although it doesn't say it, our x-axis here is time in seconds, and our vertical axis is position forward in meters, so that makes sense. But they're the same thing. Change in x over change in y, or sorry, change in y over change in x, change in d over change in t. Same thing. You can think of it either way. All right, so this means we're going to take the, again, I don't mean to confuse you, but a change in anything, I could have a change in x is going to be x2 minus x1. I could have a change in d, which is going to be d2 or d final minus d initial. A change in t is t final minus t initial. And if I was doing x's and y's, this would be y2 minus y1 over x2 minus x1. Now instead of 1's, I have i's, and instead of 2's, I have finals. So you can see how it's the exact same process as you guys went through with slopes, except I've just changed the letters. Now I need to go to my graph and find 2 points. Doesn't matter what 2 points are, as long as they're on jogger A's line, I should be okay. Kind of hard to see, but I'm going to pick this point here at the origin, or 0, 0, because I love doing calculations with zeros in them. Subtracting 0, adding 0, very easy math. So if you can ever pick a point that goes through the 0, 0, then do that. It'll make your life a lot easier in terms of calculations. And then I'll do this one up here. Those look like 2 good points. They're both on the line. Will there be questions like this where we have to convert our units? It's possible. I'm not going to rule it out. It would be kind of evil, but I wouldn't put it past the creators of our course or the creators of the provincial exam. So yeah, it's really important to kind of look at your units when you're going through this. It might ask for something different than the graph. I don't know. The fact that you're asking the question means that you know enough to watch your units to kind of be aware of it. So I think you'll be okay. I know you'll be okay. Just need to be careful. All right, so I have 2 points. This point down here is 0, 0, and I'm going to call this my initial point. So these are my I's. And then up here, I have 5, comma, so that's 20. And this is my final point. Now, this is literally exactly the same as the math questions we would have done in order to calculate the slope. So my final distance is going to be 20, or my y term, minus 0 over 5 minus 0. So I'm going to have 20 divided by 5, which is going to be 4. Now, my position is in meters, and my time was in seconds, I'll assume. So this is jogger A, 4 meters per second, and all I have here is forward for a direction. So there's not much I can do. I don't know if it's up, down, front, back, whatever it is. 4 meters per second forward. Now you're thinking to yourself, Mr. Borden, that was sure a lot of work just to find the slope. Couldn't I have just looked at the graph and said, he started 0, he went here, this was 20, a rise of 20, a run of 5, 20 divided by 5 is just going to give me 4. Yeah, for sure you could have done that, which would have been really easy. The problem with that is if the person didn't start at the 0, 0, finding the slope by just looking at the last point won't work. So if I had a line, for instance, that started here, that went to there, if I said, okay, this is 16 over 2, okay, 16 over 2, the slope of that is 8. Well, that's not true. What I would be doing is I would be going 16 minus 10, and then 2 minus 0. So 16 minus 10 over 2 minus 0 is going to give me 6 over 2, which is going to give me 3. So I can't just take the last point. I can't just take the end point. The only way I can just take the end point is if the object or the whatever I'm talking about, person, also goes through the origin. So just be careful on that. For question 2, how would we describe how we know? Are you talking about this guy? The slope of a distance versus time graph represents Speed. All right, so the slope of a distance time graph is speed. Describe 3 ways you know this to be true. I can think of one way. I could calculate the slope, and my units will be in distance versus time, which is a speed. Number 2, you could give an example, yeah, for sure. I would know how far I went in a given time. And I'm not sure what the last one. Average velocity is change in position over change in time. I would go with maybe those 3. You could give some examples, I suppose. So you could look at the units. You know how far you went in a given time. And then you could use the formula average velocity, which is the same thing as the slope, but it's perhaps a little bit different. Kind of a strange question. Obviously, they're looking for something really specific, probably out of the notes, but I don't know what they're hoping for there. So I also have one thing to ask about a part of the final question. Okay, let's keep going through here. For number 4, you're going to find the slope of jogger B next and include that. So I did A for you. You can do jogger B. The motion of a race cart on a linear track shown below. When's the cart's starting line, standing still, direction. What is the fastest speed? So when it says fastest speed, that is the steepest slope. So look for the steepest line. When does it happen? Average velocity of the cart between 0 and 20. So that's the slope again. Remember, slope is velocity. What is the average velocity of the cart of the entire trip? Have a go at F and see how you end up. I will go through that with you next day. I have a feeling a few of you will have questions on that one. So do your best there for F. Oh, that was the one that you wanted, Abby. All right, Ava. All these A names starting to get to me. Finding the average velocity, maybe I'll just give you a few hints. I guess there's a couple ways to do it. I would probably find the velocity in each time interval. Yes and no, Ava. Think about it this way. If you were driving to Vancouver and you were driving, through West Kelowna, that's a real slow go. So maybe you drove like 20 kilometers per hour for 10 minutes, and then the rest of the trip you traveled at 120 kilometers per hour. If I added those up and averaged them, I would get 140 divided by 2, so I get an average velocity of 70 kilometers per hour, but I only traveled that 20 kilometers per hour for a very short period of time, and then I traveled 120 kilometers per hour for a very long period of time. So you need to take into consideration how long you're traveling at each of the speeds. So just be careful on that. If you're traveling really slow for just a really short period of time, that shouldn't affect your entire average velocity because you only traveled slowly for a very small period of time. So given that, see what you can do. I will go over it for sure next day, Ava. So I don't want to ruin it for everyone else. I want everyone to have a go at it. See how you end up. There's more than one way to do it. So different people can do it different ways, and there's no way that's more correct than the other. I don't want to ruin it for anyone. Should you give a direction and they're different? It may not be a good idea for the final question, but should you give a direction associated with positive and negative? So remember that the positive and negative is giving a direction. If I have a positive velocity, that's the direction. If I give you a negative velocity, well, that's a direction as well. Positive is going one way. Negative means the opposite of the positive. So when you guys say, should I indicate a direction, you don't have to get caught up in the north, south, east, west, forward, up, down, left, right sort of idea. Positive and negative are indicating directions. They're relative to one another. They're relative directions, but they are indicating a direction. So if the question doesn't have an east in it or a west in it, then your answer shouldn't either. If your question says they're moving forward and your answer is positive, it's moving forward. If your answer is negative, it's moving backwards. If you have a question where it says an object's moving up and you end up with a positive answer, okay, that object's moving up. If it's a negative answer, it means it's moving down. If it doesn't give you an up, a down, a forward, a backward, a left, or a right, your answer won't have one. And that is just a kind of a limitation of the question. So you don't have to force a direction, I guess. If they give you something, your answer should include it. If they don't worry about it. Because it's positive, that's indicating its direction. So positive is a direction. I don't know what the direction is, but positive means it's going the same way as, whatever you said in the question. So you don't have to write the word positive. If your answer is positive, then that's all you're expected to do. You don't have to write positive in brackets. If your answer is positive, go with that. If your answer is negative, put that in. That's all you can do. Unless they give you a direction on a graph or in the question, you can't indicate it. So you can only work with the information you're given. You can't make something up out of nothing. And yeah, I'll just leave it at that. If they don't give you a direction, you don't have to include a direction in your answer. If numbers in the question are positive and your answer is positive, then you know it's the same direction as whatever you're starting with. Yeah, so again, when you're saying direction, I wouldn't say forward or backward. I would just say positive and negative. Positive is a direction, negative is another direction. If I'm calculating the average velocity, let's not kid ourselves, we're looking at this. This portion of the graph here has a positive slope. This portion of the graph here has a negative slope. So I don't know what this slope is, I'll just make it up. I'll say it's 10, and then I'll say this is negative 10. Well, I haven't said that this is 10 to the east, and this negative 10 means 10 to the west, but I know the directions are opposite one another because this slope is positive and this slope is negative. So the positive and negative are indicating a direction for me. And then again here I have a positive slope. So positive and negative is a direction upon itself. Doesn't necessarily need to be east-west, forward, backwards. But the slope is positive, the slope is 0, the slope is negative. The actual numbers that are positive and negative are very important. If it's going down to the right and your slope is 12, it needs to be negative 12. It can't just be 12. And it's exact same as math. If you had a negative slope, it is a negative. And if you had a positive slope, it's positive. It's just that straightforward. Again, if you had a direction, you could include it. But even in our calculations, we're not going to write in north and south or east and west. It just confuses things. We use positive and negative to indicate that they're opposite directions to one another. Hopefully that's all right. I'll go through the answers to these next day if you guys end up with questions. I know you'll have a question about F for sure. So try it, but I have a feeling most of you will want to see it done anyways. Yeah, definitely on a provincial exam, you will not be expected to, well, you could be expected to draw a graph and find the slope from it if you're given some information, but it's all multiple choice, so you're never going to be marked on your graph. It's just the answer you're going to get from your graph. So yeah, you'll never be expected to draw a graph to submit for an answer. You have multiple choice, so they could give you 4 graphs and you have to pick one, but never are your graphs going to be actually marked. All right, let's look at acceleration, chapter 9. So that ends chapter 8. I know we kind of started it and then took a break and then we came back to it, but it's not a long unit. There's not a lot of information there, a bit of calculation type stuff. Chapter 9, it looks exactly the same as chapter 8, and I'm just going to go through it like it was the same thing. Really, 8 and 9 should be together in one big test, but you get 2 little tests along the way. Okay, we've already talked about uniform motion today. Remember the pool ball that was rolling along the table with the flashes showing how far it traveled? And this is the same example here. Object traveling with uniform motion means it traveling the same distance in the same amount of time. So from 0 meters to 4 meters took 2 seconds. So that was a distance of 4 meters taking 2 seconds. The next 4 meters took 2 seconds. The next 4 meters took 2 seconds. So that is uniform motion. Now, before I asked you, what would non-uniform motion look like? And this is what it looks like. This car is going to the left. So from 0 to 2 meters, it took 2 seconds. If it were uniform motion, it should travel to 4 meters at 2 seconds, but now it's going from 2 to 8 meters in 2 seconds. So the first 2 seconds, or the first 2 meters took 2 seconds. Then 2 seconds later, now you're all the way up to 8 meters. So you've traveled 6 meters in the same amount of time. And then you travel another 2 meters in 2 seconds, and then you travel another 6 meters in 2 seconds. So you can see how the non-uniform motion looks. The object is changing its velocity. It's traveling a different distance for the same time interval. Each one of these time intervals is 2 seconds. But here it's only moving 2 meters, and then here it moved 4 meters, and here it's moved 6 meters, each of those time intervals. So that is non-uniform motion. Now we've talked about position, we've talked about change in time. Now we're going to talk about change in velocity. So change in velocity is your final velocity minus your initial velocity. We have the delta V, change in velocity. And there are 4 scenarios you can encounter with acceleration or changing in velocity. And the first couple are really straightforward because they're things that you can kind of wrap your head around. The last 2 get really confusing because the sign direction thing gets really mixed up. So let's maybe just look at them and then we'll see how we do. This is a drag race car. Describe the change in velocity. If you've ever seen a car race before, this is like a straight down the drag strip type of race. What's happening to the car's change in velocity? What velocity is it starting with? What velocity is it ending with at the end of the race? How would you describe the change in velocity? Another way to think about it is it speeding up? Is it slowing down? It's another good way to describe a change in velocity. Anyone want to describe the change in velocity? Anybody ever been to a drag race? You know that the cars start at a stoplight type thing. So they start at 0 velocity, they're not moving, and then they speed up very quickly, so they're increasing their velocity. So the change in velocity would be from 0 to something big. Now, if we think about change in velocity as the final minus the initial, the change in velocity is going to be really big. We don't want to talk about how fast, because you're implying a time there. I'm going to have to sneeze here. Trying to keep it off. Can I do it? Okay, I think I can do it. So don't think about it in terms of how fast. We're not talking about time at all here. We're talking about its velocity, how fast it's moving. We will eventually talk about how long it took, but not yet. So change of velocity. If I have a dragster, it starts at 0, it ends at, let's say, 300 kilometers per hour. That's how fast it crosses the finish line at. So what was this change? It went from 0 to 300. So if I take the final speed at the finish line, 300, and I subtract 0, its change was 300. It went from 0 to 300 kilometers per hour. Okay? How about this? Space shuttle. Well, they don't fly anymore, sadly. If it lands, what's its change in velocity going to be? How is it different than the drag car? Is it different at all? Are they the same change in velocity? Are they different changes in velocity? What is one of the fundamental differences between these two examples? So drag race car starts at 0, speeds up, goes really, really fast, and finishes the race. The space shuttle lands, and when it touches down, if you've ever been on an airplane before, same sort of thing, touches down, it's going really, really fast, and then you can see all these like speed brakes get popped out and big parachute out the back to slow it down. It would eventually stop. That's the point of landing the spaceship. If you can't stop the spaceship, well, you can't get out unless you want to just jump out of a moving space shuttle, but that's probably not a good idea. So I feel like you guys are looking for really complicated answers to really simple questions. It will have a slower velocity that goes closer to 0 on a graph. Not talking about a velocity compared to one another, not talking about graphs, just what's happening to the change in velocity. Let's say the space shuttle flying lands on the runway, it's going 500 kilometers per hour. Super, super fast. Throws that parachute out the back, the parachute slows it down, the air brakes deploy. Eventually the space shuttle is going to come to a stop. So what is its change in velocity going to be? How fast was it going? Let's say it started, touchdown at 500, and then stops. Its final velocity is what? Well, it stopped, so its final velocity was 0. What was its initial velocity? Well, I just made up 500. It's way too big, but we'll just pretend. 500. So 0 minus 500 is negative 500. The velocity changed by 500. It actually slowed down by 500 instead of sped up by 500. Sure, let's do these and then maybe we'll have some epiphanies or something. All right, how can you tell from a distance versus time graph whether a motion involves acceleration? We haven't even talked about acceleration, so we're just going to skip you for now. Question 1. Yeah, I don't want to do any of these. I've changed my mind. Don't want that, I want that. Let's just look at examples 3 and 4 here. If a car is driving along at 100 kilometers per hour, is it accelerating? We haven't even talked about acceleration yet. So let's just skip that. Acceleration. Let's talk about the definitions and then we'll go back to look at those questions. Now, before Ava, you said, is it how fast the car takes to get to its top speed? And that was kind of what we're getting to right now. So acceleration is the rate of change in velocity. It's how fast you change your velocity. So two objects with the same change in velocity can have different accelerations, which is kind of confusing, but we'll talk about that in a second. Let's think about these two cars, kind of like the drag race car we started with. Suppose these vehicles starting from rest speed up to 60 kilometers per hour. They'll have the same change in velocity. Which one of these cars is going to speed up faster? The super cool drag race car or the old-fashioned car? They can both get to 60, but which one's going to get there faster? And which one will have a greater acceleration? Is anyone out there today? I don't mind showing up to teach you guys, but if you're just gonna sit there, then we're not gonna really get anywhere. The race car, thank you, ladies. Of course, the race car is gonna get there faster. Now, if we talk about change in velocity, they're both starting from rest, or zero velocity, and they're both finishing at 60 kilometers per hour. So just talking about their change in velocity isn't enough to describe the acceleration. Now, the race car is going to get there a lot faster than the old car. So what does that mean? Well, we talk about the acceleration being the rate of change in velocity. So because the race car is getting to 60 kilometers per hour a lot faster, it's going to have a bigger acceleration. Whereas the old car, it's going to the same speed, but it's going to take longer. So it's going to have a lower acceleration. So that's a really great way to kind of think about what acceleration is. Now, if you've ever been in a car, bus, plane, when you're at a stoplight in a car, you step on the gas, you kind of get pushed back into your seat a little bit. That's what acceleration feels like. Same thing, if you're cruising in your car, you hammer on the brakes or your parents hit the brakes, and all of a sudden you go forward really, you feel yourself wanting to move forward, but the car is kind of slowing down behind you sort of thing. So that's what acceleration feels like. You can have acceleration forward from a stop line, or you can have a negative acceleration, it means you're slowing down. So velocity versus time graph acceleration will be shown by the slope being positive. Yes, that is correct. All right, so from a distance time graph, how can we describe acceleration? I still don't like that question. Let's look at examples 3 and 4 here. Example 3, car is moving along at 100 kilometers per hour. Is it accelerating? You're traveling to Vancouver, 100 kilometers per hour down the connector. Are you speeding up? Are you slowing down? No. So a car that's traveling in a straight line at 100 kilometers per hour is not accelerating. It's not speeding up, it's not slowing down. You haven't put your foot on the accelerator, you haven't hit your foot on the brake. Those two things would make you either speed up or slow down. Number 4 is a really kind of profound question in physics, which a lot of really amazing things come out of, but we kind of don't talk about that till physics 11. But imagine you were on an airplane and you had earplugs in and you had a blindfold on and you're just sitting on a plane. Would you know that you were moving if you were on a plane with a blindfold on and earplugs in? You maybe don't know how you got onto the plane, but could you tell you were moving? Or if you were in, think about like a really big bus or like a motorhome traveling down the highway, blindfold on, earplugs in. You can't see, you can't hear. Can you tell if you're moving or not? What do you think? And I'm not looking for like really small details like every time you'd go over a bump, you'd feel it, or like turbulence in an airplane, nothing like that. Feel it, yeah. No, unless there's turbulence, yeah. Perfect. So yeah, you have no way of telling, and maybe even like an elevator. If the elevator is going up or down, can you tell? You can't see out, you're completely enclosed. Could the elevator be going up when you want it to go down? Sure, you have no way of knowing until something happens. So if you're on the airplane, earplugs in, blindfold on, you wouldn't be able to tell until the airplane landed and started to slow down. Or if you're in a car or a bus, if the person were to speed up, you'd feel like you're going backwards. If the person slows down, you'd go forwards. So this is what acceleration is. I can be traveling in a car or a plane going 300 kilometers per hour, and I don't feel it. It doesn't feel any different. But as soon as the plane speeds up or slows down, I can feel that. So that's what acceleration is. And then the faster the acceleration happens, the more you can feel it. The last three sets of formulas we have are acceleration is change in velocity over change in time. And we describe this as the rate of change of velocity. So if I go to your data booklet on the bottom, you can see that we have these formulas for acceleration. Acceleration, change in velocity over time. If you want to solve for velocity, it's acceleration times time. And if you want to find time, it's velocity divided by acceleration. And then you have the three change in velocity formulas. This one's isolated for change in velocity, initial velocity, final velocity. So these are your physics formulas. This is all you'll need for chapters 8 and 9. All right, so we have a pool ball. And it's traveling at 2.5 meters per second towards the cushion, and the cushion is just the edge of the pool table here. It bounces off at 1.5 meters per second. So the ball comes in, hits the edge, and then bounces back. What was the ball's acceleration? So pool ball cruising along, boing, bounces off, goes back the other way. Yeah, if you were to live in the United States, you'd be doing all your questions in feet per second, which is a common unit there. We're not in the United States, so we do ours like the rest of the world in meters per second. All right, let's do this question. There's some really kind of weird things that come as a result of this. First thing, we need to pick a direction. Do we want right to be positive, which is different than mine, or do we want left to be positive? Well, normally we say everything going to the right is positive. So I look at my diagram, I see that this guy is going to the right, so I'm going to call this a positive direction, and then this guy is going to the left, so I will call this a negative direction. Very important we get that out of the way to start. All right. What is the ball's acceleration? The question is asking us to find the acceleration, which is a change in velocity divided by a change in time. Remember the arrows on top of these things just mean these are vectors. I could just get rid of them altogether and the question would be the same. Remember the change in velocity. Off the back of our data booklet, change in velocity is final velocity minus the initial velocity. That is a change in anything. A change in time is the final minus the initial. A change in pressure is the final minus the initial. Doesn't matter what the example is. So in this case, we need to find out what the final velocity is, and we need to figure out what the initial velocity is. Now, the reason I made these kind of sign things really important in the beginning is that my signs are different. My ball was moving to the right, hits the cushion, then it bounces off to the left. We can call it acceleration or negative acceleration, deceleration, or negative acceleration. I will try to stick with negative acceleration, but deceleration works as well. So my final velocity is negative 1.5 meters per second, and my initial velocity was 2.5 meters per second. Hopefully that makes sense. I need to differentiate between the direction these things are traveling. So if I want to find the change in velocity, I need to take the final, which I'm calling negative 1.5, and I'm going to subtract the initial, which is 2.5. So negative 1.5 minus 2.5 is negative 4 meters per second. Now this is what you guys were asking me for. Do I need to say it's to the left? Well, not really. The negative sign here tells me it's to the left. I've decided everything in my question to the right is positive, so if I have a negative, then I know it's to the left. So I want to find the acceleration. That's what the question's asking me to find. In order to find the acceleration, I needed to know what the change in velocity was, which I just found out was negative 4. This gets back to the idea of the old car and the new car accelerating. Well, they both got to 60, but the drag racing car got there a lot faster, so it had a greater acceleration. Now in the question, it tells me the time it took was 0.2 seconds. So if I wanted to find the acceleration, I'd go 40 divided by 0.2, which is going to be the same thing as 40 times 2. Negative 4 divided by 0.2. I'm a step ahead of myself here. 4 divided by 0.2 is going to give me 20 meters per second, which is kind of a really goofy unit, meters per second. What we end up doing is calling this meters per second squared. If you want to think about this, might help you a little bit. If you think about negative 20 meters per second is how fast it's changing. So 20 meters per second is a velocity. And we talk about acceleration being the rate of change in velocity. So it's how fast the object changes its velocity in a given amount of time. So what this means is negative 20 meters per second means that every second the object's changing its velocity by 20 meters per second. We also call that 20 meters per second squared, and those are the units we'll always use. But if it makes more sense to think about it as 20 meters per second every second, then go with that. So it's changing its velocity by 20 meters per second every second. That is the acceleration of this pool ball. Let's look at a few more. All right, the next question says a car accelerates from rest to 3 meters per second for 5 seconds. What's the velocity of the car at the end of 5 seconds? All right, if it accelerates from rest, this is a really important piece of information. That means your initial velocity is 0 meters per second. The other piece of information I'm given is, this should say 3.0 meters per second squared, but the superscript didn't work. So that's your acceleration. And then this guy here is a time. So I already have the formula. Change of velocity is the acceleration times the time. I know my acceleration is 3. I know my time is 5. So my change in velocity is going to be my acceleration, 3.0 meters per second squared, times a time of 5.0 seconds. So my change in velocity is going to be 3 meters per second squared. So every second, I'm changing my velocity by 3, and I'm doing that for 5 seconds. So the first second, I've changed it by 3. The second section, I'm up to 6. The third second, I'm up to 9. If I kept doing that for 5 seconds, I would end up at 15 meters per second. So if I started at 0, each second I increased my velocity by 3. I did that for 5 seconds. If you just think about it in your head, you start at 0, 3, 6, 9, 12, 15. 5 seconds later, you're at 15. If you do the actual calculation using the formula, you're going to end up with the same thing. Now I don't have a direction, so I just leave it as positive 15 meters per second. My change in velocity is going to be 15. Now we found a velocity, and velocity's units are all going to be in meters per second. What we're doing here, if you think about the math, is you have meters per second squared, and then you're multiplying it by seconds on the top. And remember, this is like seconds to the power of 1, and then you have seconds to the power of 2 on the bottom cancel. So kind of getting back to your exponent laws, you're going to end up with meters per second, not meters per second cubed, because those seconds are on the top. All right, what else do we have? Acceleration is the rate of change in velocity divided by time. An example of acceleration might be 10 meters per second each second, or 10 meters per second squared. All right, let's look at another example. A truck started from rest. As soon as I see from rest, that means my initial velocity is 0 meters per second. And it sped up at 10 meters per second every second for 5 seconds. How fast would it be going after each second? Okay, here's my truck. I have 0 seconds, I have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. All right, so my truck is accelerating. It started at 0, and then it sped up to some speed. I want to figure out the velocity at each of these times. Okay, if my car is accelerating at 10 meters per second, every second, how fast would my car, or truck I guess, be going after 1 second? Started at 0, increasing it by 10 every second. How fast am I going now? I'm going 10 meters per second. All right, what about a second later? I started at 0, now I'm going 10. Every second I'm increasing my speed by another 10. So at 2 seconds, how fast am I going? I'd be going 20. I continue to accelerate 10 meters per second squared, or 10 meters per second every second. I would eventually end up at 5 seconds traveling at 50 meters per second. So each second, the truck is increasing its velocity by 10 meters per second. That's what 10 meters per second means, or 10 meters per second squared. Okay, we can do this. Maybe I'll do one of these. We'll talk about the scenarios. Let's just talk about the scenarios. Got about 5 minutes or so left. All right. Describing acceleration. I'll come back and do some of these next day. Positive and negative acceleration. This is why acceleration can get a bit tricky, is because your acceleration can be negative sometimes. What does that mean? So if you're in a car and you're speeding up in the forward direction, this is kind of like you're at a stoplight, the light goes green, you increase your velocity. You put your foot on the accelerator, which is called an accelerator because it accelerates your car. If my velocity was going forward and my acceleration was going forward, would my car be speeding up or would my car be slowing down? What do we think? Speeding up, slowing down. The first two examples are very straightforward, and then they get trickier. For all of those of you who said speeding up, you are correct. So your car is moving forward, you're accelerating forward, your car is going to speed up. Is it possible to accelerate backwards while your car is going forwards? Yeah, that's what happens when you're driving in your car and you put your foot on the brake. Come to a red light. Your velocity is forward, your acceleration is actually backwards because you're slowing down. So this is why acceleration gets tricky, because it's kind of hard to wrap your head around that. You're moving forward, but you're changing your velocity negatively. You're slowing down. Your final velocity is going to be 0, but your initial velocity was 50 kilometers per hour. So your change in velocity is actually negative. We'll talk about graphs later. We don't want to confuse ourselves right now. So your change in velocity, because it's negative, you're going final velocity, which is 0, minus your initial, which was whatever, 50 or however fast you were traveling. Your velocity is still going forward, but your acceleration's backwards. Weird. Two other scenarios. These ones are a little bit more complicated. Now, this is kind of like the first scenario, except everything's backwards. If you're in a car, you're in reverse. You're speeding up going backwards. Has that ever happened? Sure. You drive into your garage, park your car, wake up the next morning, time to go to school. Jump in your car, put it in reverse, put your foot on the gas or the accelerator, and you start to speed up going backwards. Your velocity is backwards. Your acceleration is backwards as well. You started at 0, you started at a stop, and you increased your velocity going backwards. So both your velocity is negative and your change in velocity is negative, so your acceleration is negative. The last one is the complicated one. Let's imagine you were going backwards and you wanted to, eventually stop and go forwards. You just didn't want to drive backwards all the way to work. So you're going backwards, you put your foot on the brake and you start to slow down going backwards. Means that your velocity is backwards, but now you're accelerating forwards, which is kind of hard to comprehend. So I'm going to go back again. Now you know what to expect. You're stopped at a stoplight, you put your foot on the gas, you accelerate once it turns green. Your velocity is forward, your acceleration's forward, they're both in the same direction. Easy peasy. The next one's kind of straightforward as well. You're moving forward, the light turns red, you slow down, so you have a negative acceleration, and then you come to a stop. Your velocity and acceleration are in different directions, you're just slowing down at a stoplight. That one makes sense. How about this one? You're moving backwards and you're speeding up going backwards. That makes sense too? Maybe. The fourth scenario is you're going backwards, but now you're slowing down going backwards. So your velocity is backwards, your velocity is negative, but your acceleration's forward or positive. So those are the 4 scenarios you can encounter. All right, I'm gonna leave you guys there. Let's just take a look at the learning guide for Unit 9. You guys will be obviously trying to finish off Unit 8, get that learning guide in. You had a few questions there to do, so I won't spend a ton of time looking at this, but assuming you can get Unit 8 in the next couple days, you should have Unit 8 test written by the end of the week for sure, by Friday. This is what Unit 9 looks like. So we should be able to do the first page. Let's just keep it simple. So if you want to stay on top of things, first page of Unit 9 learning guide would be great, but obviously worry about Unit 8, getting that finished and the test written. I will begin next day's class with answers to any questions you might have had on the Unit 8 learning guide now that we've finished that up. So you should have Unit 8 learning guide polished off tonight or tomorrow. And then if you had a few questions, we'll go over them in class on Wednesday. We'll continue on with Unit 9. I hope if you guys don't have a ton of questions, we'll actually finish off Unit 9 on Wednesday, which really means we're finishing off the course, which is kind of crazy. If we have to drag it on into the following week, then that's okay. One other thing I wanted to mention is on, not this week on Wednesday, but the following week on Wednesday, I've got a lab at KSS for us, reserved, and we can go there and actually do a lab activity, which would be really fun. Get to use some really cool like handheld graphing type things, and they're called LabQuest units, so it'll be great. So if you guys want to come to that, we'll be doing that on the 8th, and I'll talk a bit about more about that next day. So I'm going to leave you there. Finish Unit 8, that's priority number 1. I'll answer questions next day on anything you had on Unit 8. We'll keep going on Unit 9 next day. I hope to finish. There's not a lot left. So we'll finish Unit 9 next day, and then we'll start reviewing from there. So have a great afternoon, and we will see you guys on Wednesday.